Hi everyone, and welcome to this first course in which we investigate number theory and cryptography. Roughly speaking, on the one hand, number theory is the study of relations between integers. On the other hand, cryptography is the science of sharing messages secretly and protecting information. I believe that cryptography is one of the most exciting applications in the intersection between mathematics and computer sciences. Before we dive into technical details, let's answer a natural question by giving a simple example. Indeed, how can we apply number theory to cryptography? Or said in other terms, how can integers protect information? Now I hope that everybody remembers division with remainder from high school algebra. For instance, if we would like to divide 13 by 4, we get 13 is 3 times 4 plus 1, and we say that 3 is the quotient and 1 is the remainder. This actually means that there are 3 4s in 13 and 1 remaining element. If you do the same thing with 21, let's say we get 21 is 5 times 4 plus 1, which also means that there are 5 4s in 21 and 1 remaining element. We say that 5 is the quotient here and 1 is remainder. Now, if you ask the exact same question about 26 and 7, we find that 26 is 3 times 7 plus 5, which means that there are 3 7s in 26 and 5 is the remainder. Notice that the remainder is all the time lesser than the divisor itself, and we get the following theorem. If a and b are both integers with b strictly positive, then there exist unique integers q for quotient and r for remainder, such that a is b times q plus r, and as we saw before, r is always strictly lesser than b. We will not prove this fact here, but instead we're going to give an amusing cryptographic application of it. Let's say there is a 13-person committee that has a vote to approve a budget. The members prefer to keep their votes anonymous. Here's a mathematical way to have every person vote yes, vote no, or abstain, while ensuring that all votes are kept secret. We'll call the president of the committee V0 and the other members V1, V2, V3 until V12. V stands here for voter. Now the procedure is as follows. V0 takes a blank piece of paper and writes on it a large number, say for instance 1729, and hands it to V1. Then to this number, V1 adds 14 to vote yes, he adds 1 to vote no, and adds 0 for abstain. V1 writes this sum on a new piece of paper and hands it to V2. Now V2 has a new number, which is either 1743 if V1 voted yes, 1730 if V1 voted no, and 1729 if V1 abstained. Because V2 does not know the original number, there is no way to know how V1 voted. This process continues with V2 adding 14 for yes, 1 for no, or 0 for an abstention, and then passing the result to V3. They continue until V12 gives a number to V0, who adds a number for his own vote. Let's say the final sum is 1832. The president subtracts the secret number 1729 from 1832 and gets 103. By the division with remainder algorithm, we get that 103 is 7 times 14 plus 5. V0 announces then that 7 people voted yes, 5 people voted no, and 1 abstention, because 7 plus 5 is 12 and the total number of voters is 13. Now one good question is, why do we count a yes vote as 14 instead of 13? It is obviously 1 more than the number of voters. If we used 13 for a yes vote, we couldn't tell the difference between 13 no votes and 1 yes plus 12 abstentions, since both give a total of 13. Actually, this voting scheme is not good in practice, because first, one has to trust the president of the committee, who can alter the final sum, and second, if V1 and V3 compare notes, they can guess how V2 voted.